The sinking of the ocean liner RMS Titanic on April 15, 1912 was one of the most dramatic events of the 20th century. The tragedy occurred when the ship collided with an iceberg, broke apart and sank to the bottom of the North Atlantic Ocean. The disaster resulted in the loss of over 1,500 lives and sent shockwaves around the world. Let's roll back a little. 5 days before, Titanic set sail on its maiden voyage over the Atlantic with 2,240 passengers and crew on board. At the time of her construction, the Titanic was the largest and most technology-advanced passenger ship in the world, with length of over 269 meters, 25 stories high, and weight of 46,000 tons. Two 16,000 horsepower steam engines and one 8,000 horsepower turbine engine powered the ship. It was a luxury passenger liner, and in 1912 everybody thought it cannot sink because of its 16 watertight compartments. These compartments were designed to be quickly closed in case of an emergency. This is DevOps undefined, and together we will explore the failures in one of the biggest engineering wonders for its time, and learn how not to sink our own DevOps projects. There were many factors that led to this disaster. Each and every one of them, important as it is, would not cause the tragic end, but combining them led to the unexpected result.
Watertight compartments.
The ship was made like an ice cube tray. If you put an ice cube tray in water, it will float. If you fill some of the ice cube areas with water, it will still be afloat, but if you continue filling more, it will sink. Titanic had in total 16 such watertight compartments that were designed to keep the ship afloat if damaged. By design, Titanic was able to stay afloat with 4 of these compartments filled with water. Filling a next one would cause the ship to sink, as the watertight compartments were not tall enough to keep the water from spilling into the other compartments.
Compromise.
The top of these compartments were open. In order to make the passenger space more convenient, the walls extended only a few feet above the waterline. Do not make compromises with your deployment security. Running services as root is not a good practice. Do a proper network segmentation and access management. Do not use default credentials and weak passwords. Do not use the same root password on all machines. Use SSH keys to authenticate remotely instead of username and password. Split the services to components. Use separate volumes, partitions, and file systems for your data. Restrict file and directory permissions. Implement least privilege approach. Reduce unnecessary services. Minimize the used software to minimize vulnerabilities.
This will never happen principle.
The ship designers thought that more than 4 watertight compartments will never be compromised at a time. However, 5 compartments were damaged after the iceberg hit, which led to spreading the flooding to additional compartments. Every component in your system will fail at some point. Design it to be highly available and redundant. Implement retries, health checks, and self-healing. Manage services lifecycle, like services startup and restart on failure.
A good engineer designs a ship that can't sink, then designs the lifeboats for when it does. It is pointless to handle this in the code.
My service will never lose connection to the database.
Single web server can handle all the load.
The ship can't sink.
But the watertight compartments were not the only engineering failure on this gigantic ship.
Sidewalls. Bad engineering design.
The ship had double bottom, but the sidewalls were made of single sheets of iron. By extending the double bottoms up the sides of the hull, the watertight compartments could remain undamaged. The addition of a layer of steel to the sides of the ship ensures that in the event of an iceberg or collision with another ship, only the space between the inner and outer sidewalls will flood with water. Implement high availability. Follow the architecture best practices.
Good intentions.
Do not overcomplicate.
If we pursue good intentions to their logical conclusion, we shall find that they lead us directly to the gates of hell.
The watertight compartments filled with water only the front part of the ship where the collision occurred. The ship pitched forward under the weight of the water in the bow. This caused extensive pressure on the hull structure as the front was underwater and the bottom was in the air. Effectively, the ship was broken to 2, which contributed to the faster sinking. Keeping the watertight compartments open could have granted some more valuable time. Making the system more resilient and highly available often adds complexity. The complexity adds more possible points of failure and should be well designed, configured, and tested.
Lifeboats. Design considerations.
The insufficient number of lifeboats aboard the Titanic was one of the most obvious design flaws. The ship had lifeboats that could only hold 1,178 passengers and crew members, leaving a significant shortage of life-saving resources. Do a proper planning of your CPU, memory, disk, and network resources. The lifeboat deployment system was overcomplicated, and the crew was not trained enough to handle it. The lifeboats had to be lowered by hand, ideally by a team of between 8 and 10 men. Despite Titanic having a number of electric winches, they could only have been used to winch the lifeboats back out of the water. Automate your deployment and define your infrastructure as a code. Not automating repetitive tasks can lead to slower delivery times and increased chances of human error. Have one code for all environments. Make the changes traceable. Store your automation code in Git. Do predictable management. Who changed what and when? What was the configuration change when the problem appeared?
False sense of invincibility. The illusion of unsinkable.
Be prepared.
The Titanic was praised as the pinnacle of engineering achievement and was thought to be virtually unsinkable. This led to lack of preparedness for such a catastrophe. There were no regular lifeboat drills or crew trainings for an emergency like this. The crew was not prepared to handle such a situation. The disorganized and inefficient evacuation process was the result of communication breakdowns, inadequate coordination, and a lack of clear instructions, which made the death toll even higher. Document changes. Have operational procedures and test them. Create backups of all your system components.
There are two types of people. Those who do backups and those who will do backups.
Test the restore process.
Backups always work. It's the restore that usually fails.
Test your system resilience.
There's a small glitch in the display of our critical life support system.
Have you tried turning it off and on again?
Driving too fast in dangerous waters.
The Titanic was traveling through a region known for its dangerous icebergs at high speed. The choice to keep the speed, regardless of alerts from different boats, had a huge calculate to the impact. With his mass of 46,000 tons, Titanic rushed with 22 knots through the darkness. By the time the massive iceberg was spotted, it was only less than a quarter of a mile off the bow of the ship, making the crash into the iceberg unavoidable. Test your changes before going to production. Having separate environments for development and testing is the best practice. Automate your tests. Fail the workflow in case of test failure.
Radio communication. Neglecting messages.
Despite Titanic had a remote message framework, it was not monitored constantly. As a result, the bridge did not receive timely iceberg warnings from nearby ships, denying the crew important information. Implement monitoring and alerting. Monitor CPU, memory, disk, and network resources. Monitor log files. The radio communication was used primarily to send passenger messages, although they were supposed to prioritize on government and navigational messages. The operators of the radio equipment were tired and overwhelmed by their work, and thus they also neglected some of the iceberg warnings received. Do not overflood the alerting with meaningless messages. SS Californian was 5 miles away during the incident and saw firing rockets from Titanic. SS California's captain didn't recognize those rockets were a sign that the ship was in distress and assumed it was company ships signaling one another. He failed to double-check the reason for the rockets firing, as the SS California's wireless operator was not on duty during that time. Set severity levels on your alerts. Make alerts actionable. Knowing what's wrong is good, knowing what to do next is better. And finally, the suspected culprit for the ship's hull failure was one of Titanic's smallest components, the 3 million rough iron rivets used to hold the hull sections together. Those rivets were made up of iron with high concentrate of slag, a residue that can cause splitting in the metal. A special tool was used to place the rivets in place in the upper sections of the ship. Going to the bottom part and in complex areas of the hull, the riveting machine could not be positioned. This necessitated hand riveting with rivets made from much softer material and with higher percentage of slag. This can explain the breakage Titanic experienced after the impact of the iceberg. Use the right tools. From development to automation, deployment, testing, monitoring and backup, there are multiple tools and applications, and all of them can get the job done. But choosing the right one for the specific use case is critical and will carve the way forward. Implementing tools that don't fit can complicate processes rather than streamline them.
Failure to learn from mistakes.
Despite several previous maritime disasters, the Titanic's builders did not implement sufficient safety measures. Do iterations and improve your code and infrastructure. Failing to continuously improve processes, tools and skills can lead to stagnation. Titanic's tragic sinking holds important lessons. It is in our interest to learn from them and try not to make the same mistakes again. At some point, safety is just pure waste. I mean, if you just want to be safe, don't get out of bed, don't get in your car, don't do anything. Thanks for watching. It is your turn. Please share in the comments your views on the Titanic mistakes and subscribe for future videos.